So we're gonna start today talking about generative models. What has happened so far, right? So we talked about, previously, what we talked about before. Previously, we talked about deep learning, artificial neural network, and what is the depth about. And later on, we actually learned some theory about the universal representability, right? About the function and the gradient, right? But at the beginning, we talked about conceptually, right? This what's a big deal about the nonlinearity depths, and then we talked about MLP can be used for general vectors. Then we started asking, can we use MLP for images like grid data? We asked that question, and we understand why it may not be a good idea. Then we ask how we utilize the structure better for the visual tasks, and that motivated us to look into the convolutional neural networks, right? And we learned that convolutional neural networks is more than just introducing a convolution. It actually addresses so many problems. It has a very small kernel matrix that can be learned. In other words, a small amount of parameters are shared. And we have a lot of other kind of operations like pooling, right, which is like kernel, but it's not learnable parameters. So, it's just average, mean pooling, or max pooling, right? And there are all other kind of operations, right? So after a couple of lectures about CNN, we started asking about what about the sequence data? What is the unique challenge for the sequence data as you can encounter in natural language processing, right? We talked about how recurrent neural networks can address such needs, right? But what challenges might be faced, right? Because between CNN and RNN, we actually spent a lot of time talking about the computation for deep neural networks, right? Because there's a forward propagation, right, defined by your model. But then to solve the optimal parameters, you have to do the backward, right, back propagation to get the gradient, right? And that actually faces the so-called vanishing or exploding gradient problems much more so than in RNN than in other kind of architectures because of the recurrency, right? Remember, we had to keep multiplying some matrices to get the gradient with regard of the loss with regard to the earlier layers, right? And especially in the language models, if you have a small gradient, a vanishing gradient, right? Then you don't know whether that is supposed to be the case. That is, a sequentially far away word has little impact to the current word, or it's not supposed to be that way. Just computationally, we have seriously underestimated the gradient, right? Because of the vanishing gradient problem. So that's why people try to, introduce some limited, right? Limited recency. So in this sense, you keep doing this in a long short-term memory or GRUs, which is more or less addressing these or alleviating these vanishing gradient issues, right? And we also talked about encoder-decoder before we talk about transformers, right? But then in the last 3 lectures, we started asking about, well, let's still talk about natural language processing, right? So what is pros and cons, right? What if we use CNN? What if we use RNN? And what if we use something called attention or self-attention? We compare them, right? So the pros and the cons, right? So one of the biggest cons about RNN is that this backpropagation cannot be done parallelizable because you are basically enforcing that sequential computation, right? This may not be a good idea for very long sentences, even though conceptually, right, RNN is addressing or looking at the whole sentence. If you look at the last hidden vector, right, h sub t, right? But it cannot be parallelizable. So if you look at CNN or self-attention, they basically use a lot of, matrix multiplication, which are highly parallelizable, right? And of course, we know that transformer actually, in the architecture, doesn't care about the order in the sequence, right? So actually, you had to use the positional encoding to embed that information, right? And how you do that is still a part of the science, right? So in fact, if you look at the Vaswani 2017 paper, they actually, of course, they designed a positional encoding function, but they didn't just concatenate the positional encodings to the input features. They actually added the positional encoding to the input features. I cannot say that I 100% understand what is going on there. So there's a lot of trick and still a lot of things to be figured out. But we also learned that, well, this attention, self-attention, right? Self-attention within encoder or decoder and cross-attention between encoder and decoders, they can, of course, they are highly parallelizable. They also have the con of the high memory demand, but hopefully GPUs are getting better and better. But one thing you want to realize is that, transformers started more or less from NLP, but its impact is going beyond NLP because people are, of course, excited at designing architectures for different kind of input data, but they're also wondering in the meantime, just like what Einstein was trying to do in the end of his career, can I find something to unite, the learning of different data, right? Is there anything universal, right? So transformers actually were regarded as one of the most promising candidates for that kind of universal representation learning. So we'll see later toward the end that apparently transformers are now applied to not just text, but also images and graphs, right? And there are theoretical analysis about that, right? And one example you saw last time was that I can just split the image into 16 by 16 pixels, and treat them as 256 words, right? Of course, that I need to make sure that I give the positional encoding of each of these 256 words, right? When I feed them to a transformer, because what transformer sees is just these 256 words, right, in a row. So they don't exactly know where the original context was coming from, okay? So today we're gonna, start talking about generative models versus discriminative models, and so this is what is the outline. So I'll first tell you what is the concept of generative models and what is motivation of doing that. We're going to talk about two major types of generative models, VAE and GAN, but be aware that VAE and GAN, right, are names of general types of models. So their components can be replaced, or I'm sorry, their components can be instantiated by any of the architectures that you have learned. For instance, VAE has encoder-decoder. We have learned before that the encoder-decoders could be CNN, could be transformers, right? In the case of the GAN, you have the generator and the discriminator, or the generator and the critique, right? Both blocks can be constructed using the foundational architectures you have learned before: CNN, transformers, RNN, and so on, right? So we'll actually include at the end 3 case studies, right, in the journal club, right? So first one is a GAN model. that will learn the distribution of protein sequences within a family. And then we can do the sampling to generate sequences or design protein sequences, right? But you see that this is a self-attention based again, meaning that the generator or the discriminator or both of them are using self-attentions, right? So it's just like the components are replaced by transformers instead of RNNs, okay? In the early days, we used the RNNs, right? And then there's another kind of generation, right? You start with, it's like a conditional generation. You start with the desired small molecule property, and then you are generating the drugs represented as graphs. Okay, this is graph generation with desired property in mind. So this is done by RL, reinforcement learning. And we haven't talked about reinforcement learning. We'll briefly mention it. But the policy network in the reinforcement learning was modeled by a graph convolutional neural network, okay? Which is compatible with the fact that the drugs are represented as graphs, okay? Lastly, we have the example. This should be the last journal club presentation, where you condition on the desired protein binding site, then you can grow 3D densities of drugs out of that desired binding site. The way you do it is you will have an equivariant neural network, which is compatible with the 3D, right? And then you do some autoregressive sampling to generate the drugs identities. So that would be the last journal club. And before this journal club presentation, we will have one journal club presentation that is using the equivariant neural networks, but not for generative modeling, for discriminative modeling, okay? So I think those two talks, the last two, will be probably both on next Thursday, which is the last lecture. Keep in mind that the week after the next week would be the final week. And we'll have the final project presentation that week, and the final project reports due a few days after that, okay? And I've already scheduled with some of you to have meetings this week and already met with some of you, so look forward to catch up. I read your midterm reports and looks like things are going on well. I look forward to working with you together and have a strong finish of the semester. Of course, we are more than welcome to continue working with us after the semester if you want to get more out of it, whether it's training or paper. We'll be happy to work together. So this is what I was talking about. So today at the end, Do-Young will talk about a GAN model, okay, for protein sequence generation. And next Tuesday, Rujie will talk about RL-based drug design. And next Thursday, we have two talks. We probably have only two talks that Thursday. Maybe we don't have more lectures. That should be the last lecture. Okay, so this is where we are. So I said what we talked about before, and except the encoder decoder, right? Except the encoder decoder. So far, we have been using MLP, CNN, RNN, or transformers to predict labels for data, right? So in other words, one example is can you discriminate between dogs and cats when you are facing a bunch of images, right? Can you tell them apart? With this, which one is for dogs and which one is for cats? So that's why we call it discriminative models, right? Can we tell things apart? But you can also do something else more than that, okay? And machine learning can do so much more than that, just giving a label, right? We can model the distribution of the data. After all, we are learning the distribution of the data, right? What do I mean by learning the distribution of data? Remember the deep fakes, right? Right? Essentially, the way we generate those deep fakes are, through learning the distribution of natural images or natural videos or smiles or whatever kind of data, and then we can sample from the model the distribution, right? And then that's how we generate the deep fakes. So the core is the distribution of the data, right? Remember last time we also talked about how to do pre-training and the 3 ways you can interact with pre-training, right? One way is to utilize, learn the distribution, right? So this is, remember for the decoder, we can use the decoder who has learned the distribution and then sample the sequences, for instance, in an auto regressive way, right? So this is what this lectures will be about, okay? So the concept, what exactly is discriminative versus generative? Let me first start with discriminative versus generative classifiers, okay? Just imagine that X are images and Y are labels like dogs or cats, right? So the discriminative model is basically trying to find out the distribution of Y given X, okay? You're saying that, no, I'm not exactly making that prediction. I just need to tell whether Y is 0 or 1. Well, don't forget that, for instance, we usually give a probability as a prediction, right? Like the softmax, right? So or logistic regression even, right? It's giving the probability, right? So this is, what is this called? POY given X. Huh? Yeah, it's a conditional distribution of Y given X, right? So, if X were the model parameters and Y are XY or data, then this is called what? Likelihood? Is it? Okay, so in this way, we're directly modeling the decision boundary, okay? You have seen this before, how supported vector machine is modeling this. Logistic regression is modeling this, or KNN is modeling this, right? So the generative model is trying to model the joint distribution of X and Y, or equivalently, because the joint distribution can be factorized by P of X times P of Y given X, or P of Y times P of X given Y, right? So in other words, it's equivalent to modeling P of Y given X, okay? So we have seen some of the models like naive Bayes or linear discriminant analysis generating this kind of distribution, okay? Why do we want to do generative versus discriminative models? I'll give you one practical example, right? Imagine that I am trying to use the AI tools or machine learning model tools to find a drug candidate. Imagine that when COVID first hit us, right? We realized that, there's a spike protein and there's other kind of proteins of this virus that can be targeted, right? Then we need to figure out what small molecules can be drug candidates and affect on those viral protein targets, right? You have to understand that the library of possible drug candidates is huge, right? Theoretically, it's 10 to 60 small molecules that can be, drug candidates. For specific protein targets, that number could be smaller, but in short, it's really like finding a needle in a haystack, right? Haystack. So imagine that, some of, you have 10 to 60, right? This is your haystack. And some of them, like 10, might be a good candidate for this SARS-CoV-2 spike protein, right? The question is, how can you find it quickly? You say that, don't worry, right? For each X sub I, where I goes from 1 to 10 to 60, my deep learning model can give me P of Y given X. The probability that the X sub I can bind to the target protein, right? And then I'm using, neural networks and GPU, so it's going to be very fast. So 1 second, every second, I can screen or evaluate 10 to 4 X sub i's, okay? That's really quick, right? But how long does it take to go through 10 to 60 all over? That's 10 to 60 divided by 10 to 4, that's 10 to 56 seconds. So it's still a long time, right? In other words, you are probably finding the needle in the haystack in a smarter way. You're not using your naked eyes, right? Like doing experiments, which takes even longer. But you have a magnet called discriminative AI models, right? You can use this magnet and go through the haystack and find the needle much faster, but it's a giant haystack, okay? So instead, you may ask, how can I do it better, right? Can I directly model the distribution of the needles directly, and then sample from that distribution, and then I can generate the perfect needle. So that's an example why we want to do that, okay? Why we want to do the generative modeling. So in the case of the generative modeling for unsupervised learning, right, there's there are much more than the supervised tasks, right? So for instance, even for a data set without labels, right, this is another reason you want to do it. We may want to construct a model like a generative network, right, that captures the characteristics of the data, which is unsupervised learning, right? In this, how do you do that? You will have to estimate the parameters of the distribution or directly generating the synthetic samples. These are two ways that you can reconstruct the data distribution, okay? And these two ways, let's look at them again. Estimating the parameters of a given distribution, like Gaussian, you just have to estimate the mean and the standard deviation, okay? Or directly generating synthetic samples without having the analytical or explicitly modeled distribution. These are two ways you can do that, okay? These two ways actually correspond to the two types of generative models we are talking about today and Thursday. One is VAE, variational autoencoder, which is actually estimating the parameters of standard of Gaussian distributions. Then there's GAN, that actually directly generate synthetic samples. Okay, these are two ways you can model, you can capture the data characteristics. All right, so let's talk about the generator, right? So let's talk about a very simple example. So the data is following a Gaussian distribution, which with mu and the covariance matrix sigma, right? And then what you can do is that you can start with a latent variable. Let's call it a z, right? Which is a standard Gaussian, right? Standard Gaussian. And then how do you start with z and then generate data x that is following the data distribution? Well, it's very simple. We all have learned, right? Just do a linear transformation from z, right? Right? But this is just a very simple example where you know mu and sigma, and you know that is a Gaussian already, and you know how to construct G, the generator, right, from Z to X. That is very simple. But in general, we need to learn the distribution of the data P of X first. Okay? So what is the idea? So the idea is the following, okay? So the idea is that let's learn this G of Z, right? Let's learn a generator G of Z, right? Using some models for this conditional distribution, right? For instance, for the probability that xi equal to 1 given z, let's call it a gzi. And then, in this, if that is the case, right, then the probability distribution of x is exactly, let's look at this one again, is what? the expectation of the conditional distribution marginalized over the distribution of Z. This is not magic. What is this? In probability, what is it called? Yes, but what P of X equal to the expectation is basically telling. Huh? Yeah, marginalization or total probability, right? Right? This is nothing but total probability, right? So this idea is sounds simple, but it's actually theoretically grounded. Let's look at it again, right? So for a given Z, right, the chance that xi equal to 1, meaning that, this is, from the, actual data, right? So essentially what it's trying to say is that, well, your G of Z actually, this needs to be constructed in this way. So in this way, you can bridge the desired P and your modeled G, okay? And we'll talk about how specifically you do that. Okay, then how do you train a generator, right? I said they are bridged, and you want to learn this generator G of Z, right? So something we have learned in the feed-forward neural networks in the supervised learning. One idea we have learned was that we use the gradient a lot, right, for the training. So gradient is a good thing, right? So if we want to train this G of Z, right, this generator model, can we make it differentiable? So you see that nowadays people talk about the end-to-end differentiable neural network a lot, right? So here, you definitely want to have something that is differentiable, so that you can train this generator neural network, okay? But how do you do that? How do you do that? Well, in the supervised learning, it's easy because for each given input X, you have the output Y, right? So in those cases, you can get the loss, which is like, cross entropy or mean squared error, right? But in our case, we are doing unsupervised learning, right? We do have the desired output, which is X, the data that looks, the deep fake that looks like real data. And, but what is the input Z, right? Which Z should be paired with output X, right? Right, like in your case, you start with a random noise, and then G of X will generate, G of Z will generate X, which is a protein-like amino acid sequence, right? So we have to find a way to train G of Z given the training X, okay, the training data. We have encountered this kind of problems before in the last lecture, for instance, in the pre-training. We also had to construct, in those cases, the self-supervised learning, right? In those cases, like, the masked language modeling, right? You mask some words out and then you have to reconstruct them, or you put two sentences together and ask whether they were born to be like, neighbors in the text, or they were just randomly put together, right? You can construct those self-supervised tasks, okay? Now let's look at, in this case, right, how do we train these, differentiable generator networks, right? So how do you train a generator? Well, the other hint from the supervised learning, right, besides the gradient, right, is that, these discriminative models are very powerful already. So can we use the discriminative models when we try to train a generator, right? So how do we do that? Specifically, I'm saying that you can pair the generator that is to be trained in a differentiable way, right? The differentiable generator, which is to be trained with gradients, you can pair it with a discriminative model. Okay? The difference between the VAE and GAN is that VAE uses a discriminative model for inference, okay? And GAN uses a discriminative model for classification. That is the difference between the two, okay? Let's keep that in mind, and we'll talk about the details of these two methods, and then let's try to chew those or digest these words again, okay? I hope you keep this in mind. Have a high level of understanding, because it's very easy to observe what other people do. In other words, it's very easy to observe the hands of others and figure out the details. But I want you to get into their brains and figure out how did they come up with those procedures? How did they come up with these models? That's more important. Okay, so let's keep these two things in mind, okay? The two things we actually borrowed from the discriminative models when we are trying to do the generative modeling, okay? One is differentiable, one is the discriminative models can be utilized actually when you are trying to train a generator. Okay, so a little bit taxonomy of generative models, right? So as I said, you could have the models of the explicit or the implicit density. The VAE is one type of generative models that explicitly model that distribution, okay? And actually, it falls below this approximate density. It's approximate because it's trying to model the distribution and to fit it to a Gaussian. So it's, in that sense, it's approximate, right? There are other more sophisticated methods that are doing, doing more tractable density, right? And then another type, as I said earlier, is you don't have to model the distribution explicitly, but you just need to do that implicitly. One way is you will generate samples directly without going through the explicit density, okay? So GAN is one of such examples, okay? So, but keep in mind that, the world is way bigger than VAE and GAN, and you have to think about, look at them like 30,000 miles high and understand that where they are in this landscape. This helps you understand what else is out there and how they just, came up.